previous videos that we would look at something called fuzzing to find out how many characters we need to create a crash. In the previous section, we just gave it 1,100 characters in our exploit skeleton, and that made a crash, and we just followed that pattern for the rest of the section. But this time we are going to send it various input and see if we can get a crash. So the exploit skeleton, or well, fuzzer skeleton, is called 3comfuzzer.py, and it is included with the course material. So again, we have a basic little skeleton here that we'll use to create our exploit once we get it to crash. So we can take a look at it. 3comfuzzer.py. So this is going to be exploiting TFTP. So we're going to use trivial FTP here on against our Windows XP system. It does have a TFTP service running. And we again have import socket, and then we have buffer array equals a times 100. We have addition equals 200. Now we have a while loop. Remember, in Python, our loops are denoted with indentation, so these two indented lines are part of that loop. So while the length of buffer array is less than or equal to 50, you might say, well, the length of buffer array is 100, a times 100. Well, since it's an array, we've got those brackets around it, its actual length is one element, so it's currently length 1. So that is less than or equal to 50. So it says buffer array.append a times addition. So addition is 200. So we're appending a times 200, and then addition plus equals 100. So addition was 200, now it's going to be equal to 300. So go through the while loop again. The length of buffer array will be 2. So we will append a times addition. Addition is now 300. And then we will add another 100 to addition. So addition will be 400. Go through the while loop again. Buffer array is length 3. So we'll append a times 400 and up addition to 500. You can see where this goes. Once it gets to be greater than 50 in length, the while loop will finish. And we'll say for value in buffer array, TFTP packet. Well, what on earth is that? I guess we need to know what a TFTP packet looks like. TFTP is a UDP protocol, so it won't set up a connection. So let's actually take a look. So let's open up our Iceweasel and look for our TFTP request for comment. So TFTP RFC should give us details about the TFTP protocol if we aren't familiar with it. Come down a little bit. Should have. Here are the types of operations against TFTP, and here is what the packet looks like. So 2 bytes of opcode. Again, these are the opcodes. So 1 is read, 2 is write, 3 is data, 4 is acknowledgement, and 5 is error. So 2 bytes of the opcode. Then we have a string for the file name, 1 byte of null to denote the end of the file name, then the mode, which again is a string, and then 1 byte of null for the end of the packet. It says down here, the mode field contains the string net ASCII, octet, or mail. So the program probably expects that the mode field will be 1, 2, 3, 4, 5, 6, 7, 8 characters or less, since those are the only 3 valid values. So that might be a good place for us to see if we can create a buffer overflow condition. File name may also be a good place. I mean, chances are the file name isn't expected to be too long, so that might be another place we could fuzz, but in this particular example, we're going to look at the mode. We're going to send varying length input to the mode field. Alright, so now this should start to make more sense. So let's look back here at TFTP packet. So I'll pull this over here so we can see this packet. So TFTP packet is, I did this in hex for whatever reason, null and then 02. So that is our 2 bytes of opcode here, and that is a write request. And then we should have the file name. So the file name here is Georgia, so I just gave it the file name Georgia. Then 1 byte of null, 1 byte of null. string mode, that's where we're going to fuzz. So we have 4 value in buffer array, so it's going to take a times 100, then the next round it's going to do a times 200, so on and so forth. And then finally the null at the end. So this is indeed a valid TFTP packet. We've just put nonsense garbage in the mode value. We print out fuzzing with length and then the length of value. So it'll say fuzzing with length 100 and fuzzing with length 200, so on and so forth. Also have print TFTP packet here. We can take that out or just print out the packet. Let's put more things on the screen that we don't necessarily need. Our socket setup is a little bit different here because this is a UDP socket. So again, I would just Google that if I wasn't familiar with what the syntax was right off the top of my head. No reason to remember stuff like that we can just Google. And then we do s.send to here. So again, this is connectionless, so it's a little bit different. We're going to send it that TFTP packet, and we do need to change this IP address to the IP address of our Windows XP system. So set yours accordingly, and port 69 is indeed TFTP. We have our response. If we get a response, we will print it out to the screen, and then the for loop will go through again. So, pretty simple there. Really the only thing we have to change is the IP address. I also took out that line where it just prints out the packet. You can leave it in. It will print out the packet each time to the screen, so leave it in or take it out as you please. Go ahead and save that and make it executable if it isn't. Oops, chmod. Alright, so now we need XP. And the TFTP service is indeed a service, so if we just open up Immunity Debugger and attach, and we look for UDP69, it's 3C TFTP SVC, so 3COM TFTP service, and it is listening on port 69, so we'll attach. It pauses when we attach, so click play, and it's running. And let's run this 3com buzzer.py. Alright, so we got, it prints out fuzzing with length 100, writes back unknown or unsupported transport mode, lots of A's, fuzzing with length 200, unknown or unsupported transport mode, even more A's, so on and so forth. We get down to 500, it looks like it didn't manage to print out unknown or unsupported transport mode, or transfer mode rather, and then when we do fuzzing with length 600, it doesn't write back at all. Alright, so we can go ahead and stop this with Control C. If we come back over to Immunity Debugger, it looks like we have an access violation when executing 41, 41, 41, 41. So typical there, EIP overwritten with our A's. Looks like we control ESI, as well as we have a little bit of ESP as well, not much in there. But was it 500 or 600 A's that crashed it? Again, it doesn't write back anything when we send 600, and it writes back something a bit different when we do 500. So it could be either 500 or 600 A's that crashed it. Alright, so let's go ahead and restart. This one does not restart nicely in Immunity. I mentioned that sometime that's going to happen. So we'll just exit out of Immunity, and we can restart the TFTP service. It is installed at C Windows. So we have this 3COM TFTP service controller, this blue and white 3. If we open that up and do start service, it will restart the service. So then if we reopen Immunity and attach, if I have the controller open, you'll actually see there are 2 processes for 3COM. So we have the controller here as well as the service here. We want to make sure we attach to the one that is listening on port 69. If we don't, our exploit won't work. Or, well, I guess it's still a fuzzer at this point. If we attach, hit play. Alright, so let's see whether it's 500 or 600 A's. Alright, so I'm just going to copy my fuzzer. I might want a copy of it later, so I'm just going to copy it to 3com exploit.py. and open up 3com exploit. Alright, so first thing, I just want buffer array to be, let's just call it buffer. And it's not going to be an array anymore, so I'll take the brackets away. And let's start with A times 600. Again, it's either 600 or 500 A's that crashed it. Let's try 600 first. We don't need addition anymore. Actually, we don't need this while loop. We're only going to send it one value. We already fuzzed it. Now we just want to verify which one of our strings crashed it. So we'll just get rid of all of that. And then we have our for loop. And since we're only going to send one string over, we don't need a for loop at all. But remember that our loops are designated by our indentation. So we need to put all of this over. So we need our TFTP packet. We need to change value to buffer. We don't really need to print out the length. We know how long it is. We do need the socket, of course, and we need to send. And we can print our response as well. So just put all of these lines over at the base. We don't want any indentation. So buffer equals A times 600. We will send buffer in the mode field. And other than that, it's all just socket setup and sending. So let's go ahead and send this. No response is what we got last time. And if we come over here, it looks like it didn't crash. It's still running. So oddly enough, 600 A's didn't crash it. You'd think if it crashed with one length, anything longer than that would also make it crash. But that's not always the case. You may trigger a completely different part of the program if you send something that's significantly longer. It really just depends. We'd have to do some reverse engineering to figure out exactly what's going on. Well, let's try this again. Make it A times 500. So we got that same response where it looks like it tried to say unknown transfer mode, but it couldn't. It says and then stops. And if we come over here, we do get our access violation when executing 41, 41, 41, 41. So we have got EIP control. We have control of the ESI register with what looks like a long string of A's and a short string of A's in ESP. So ESP looks like it's right at the end here. You might say, well, we could use ESP again. We just send it a longer string, right? Well, we just saw if we just gave it 100 characters more, it didn't crash at all. So we've got a few A's here. So even with 100 A's more at the end, it wouldn't crash. So chances are ESP is not going to be a good choice for shellcode. Looks like we have significantly more room here at ESI. So we might, instead of jumping to ESP, this time we might want to use ESI. Alright, so I'm going to leave it to you as an exercise to see if you can turn this into a working exploit. Before I do, let me open up Notepad very quickly. And let's think about what we need to do in order to make a working exploit. Let's make that a little bit bigger than that. 12 is not very big. Alright, so we want to find which A's are in EIP. So we will do a Mona pattern underscore create. And then 500, since we want it to be linked 500 this time. And then after we've caused the crash, we want Mona find MSP. And that will find the offset to EIP and the offset to ESI, which again is the register we want to jump to. Then find a jump or equivalent to ESI register. So it's going to be Mona JMP -R for the register and ESI. And we can do that CPB. I always get that wrong with B at the end. I have to remember that. And the only bad character in this one, I'll give you the bad characters here as well. There's a blog post at my website at bulbsecurity.com that has information about how to find bad characters if you're interested. We're not going to cover that in this class. but the only bad character for this one is the null byte, so that's the only one we have to avoid. And don't forget to make it little endian. And then we need to generate some shellcode, which is going to be MSF Venom, payload, some payload, and space, however much space you have, and bad is going to be 0, 0, and format is, well, kind of running out of room here. So bad, null byte, and then we need format is Python, and offsets will be important here. And since we're using ESI as our register to jump through, we shouldn't have any problem with it decoding itself with Shikata Ganai. Of course, if it does crash by any means, you should certainly try and debug what's making it crash, but you shouldn't have to do any metasm here. The shellcode should just be able to decode itself fine. Just make sure you avoid the null byte in the original shellcode with the -b. But you will see that the shellcode actually goes at the beginning here and not at the end, as it was with WarFTP, so our offsets are going to be very important. So if we only give it, say, 376 bytes of shellcode, but we have, say, 500, well, obviously not 500, but say 450 bytes before our return address, and we don't put some padding there, then our jump will be in the wrong place, and we'll probably get a crash, and we certainly won't get a working exploit. So it is very important to keep track of your offsets with this one, since our shellcode will be before the return address. So I will leave this to you as an exercise. It's very similar to the one we worked through together. So this is fuzzing, and so we just sent it longer and longer input until we got a crash, and even going longer than that, it stopped crashing. So it was just a small window that we were able to create a crash. And now we're going to see if we can turn it into an exploit using these steps.